Okay, the goal of this video is to show you a wave pulse traveling on a string and look at workbook problem 16.2 on page 24. So let's start right here. Just have a rope. It's tied to that stand over there. And I believe, if I'm not mistaken, I can just barely see. So I'm just barely in the frame. So the idea is, this is going to be a little bit exaggerated, but you can imagine sending a pulse down the string. If I whip it, you could see that pulse traveling to the other end, right? Now, in this case, it gets wild and kind of out of control because there's not much tension on the rope, but you can see a pulse traveling down the rope. Now, if I add a little bit of tension here, let's let the string calm down for a second. So I'm going to pull on this slightly, putting this under tension. Now what I'm going to do is just flick the rope. Oh my gosh, I have so much marker on my fingers from erasing the board to get ready for this video. Sorry about that. Anyways, I'm going to I'm going to flick the string upward, and you should see a pulse rapidly travel back and forth. There's a lot of tension, which increases the wave speed. And so hopefully that shows up on the video. So all I'm doing is I'm stretching the string upwards. And this is kind of a more realistic example, but it's hard to see on a video. So again, instead of doing this huge pulse that travels slowly because there's not much tension, in a real life situation, you're usually going to have a lot of tension here, and you're going to pluck it. And the amplitude of the wave pulse, the height of the displacement of the string, is much smaller than the length of the string. So here it's so small, you probably are having trouble seeing that on the video. Let's go to the board and talk about this. I suppose I should probably do this. Get this thing out of the way, and probably this thing out of the way too. Now let's go up to the board here. All right, so here we saw, now I think just a second ago, I was flipping the string from this end. So just imagine the video was mirrored. And so imagine I flicked the pulse and sent the wave down this way. All right, and so there's going to be V, which is the wave speed. That's the speed at which the pulse travels, or which the energy travels, right? This pulse is carrying energy with it. Like if this hit you in the face, it would hurt, right? The string flicks you in the face, you'd be like, ouch. All right. Here we say y is a function of both space and time. The vertical, oh, whoops. Where's my other marker? This equation depends on time, right? So the vertical position of the string will depend on which part of the string you're talking about, what x value, and what time, okay? And so these equations for wave pulses must be of the form, I should be careful here, plus or minus, and let's put these parens in purple here. Okay. The plus sign means you're traveling left. Minus is traveling right. So these equations, y of x of t for wave pulses, are always in this form, where it's the x plus or minus vt, and this has to be grouped together. I'll have another video in a second that kind of emphasizes this, and in that video we'll discuss, you can also find out that this can be of the form y is kx minus omega t, and in the other video I'll explain what all this means. There's a little bit of glare there, let's get rid of that. Sorry about that. All right. So now let's just try and use this information and imagine we're looking at a string wave. Let's look at problem 16.2 and see if any of this makes sense. All right. Here we see an equation that is of the form, anywhere x appears, it's always x minus vt, right? And so good, that shows up on the screen. So this is a crude model of me flicking the string and it traveling down. Now, to make this problem a little bit easier, look at a couple of things on the scales here. This is 0 to 100 meters. So that would be, a football field long, right? And notice the height here, the vertical scale is exaggerated by a factor of, I don't know, about 50 or so. Anyways, so this is 1 meter up and down. So this is what I was trying to say. When you have the string under tension, you can't really see the wave pulse that well. You can maybe see a slight disturbance. And so here I'm zooming in on the vertical axis to kind of make the wave pulse stand out. And this is just a totally bogus equation I made up. We could talk about more realistic ones in another video. But so in this case, what are we supposed to figure out? The units on A and B and the speed of this wave pulse. All right, so in this case, let's start with the units of A and B. And think to yourself how you'd approach that. If you want to pause the video, great. Otherwise, I'm going to go right into it now. So pick one of the symbols, A or B, and attack. Now, in this case, I'm probably going to start with the symbol for B. Or this variable B, or constant B, and I want to figure out the units of that. Why would I start there? I know that B is added to this thing. Whenever you add two things together, you have to add apples to apples, oranges to oranges. We know that these two things must have the same units. Well, I can tell the units of this thing. This is meters per second times seconds. That's meters. Where's my black marker? Here's one. This is meters, right? But it's squared. So the units of B must be meters squared. Now I'm going to attack A. Well, I can actually see that this thing all over here has to be in units of meters. So if this is in meters, this whole thing must be in meters. The denominator has units of meters squared. That means this must be meters cubed. So let's think. If you plugged in a value for X, you get something with meters squared. You'd add it to B. Meters squared plus meters squared makes sense. A divided by this garbage on the bottom had better leave you with meters, so I need meters cubed. So that's how you get the units of A and B. All right, next. How do I get the wave speed? All right, well, remember, wave speed is the rate at which the pulse or the energy is traveling down the rope. I would use this distance right here. Well, if you want to pause the video, go for it. I guess it's too late. I may have ruined it. Notice this distance is 20 meters. Right? And is that showing up? Yeah, just barely. So the wave is traveling 20 meters in how much time? Oops. I'm going to stick an extra 0 on here because I'm feeling lazy and I don't want to think about sig figs. So in this amount, okay, so this, you could call this T1 and T2. Delta T is equal to T2 minus T1, which, what is that? 0.667 seconds. Normally I write S, but it was kind of looking like the 3. So yeah, you could just write the letter S for seconds. I don't know why, I was just tired. Right? So, oh, I think I already did that. Okay, just making sure I didn't screw up there. So now we can get the wave velocity is this 20 meter distance. We'll call this D. It's just D over delta T, which in this case, what was it, 20? So I got about and then depending where, right, so you could argue if I didn't have this 0, we'd really only have about 2 sig figs. So we could round it to here or there, depending on how many sig figs. So let's just go to there. We got 29.99. So we'll just round it to that. So that's how you get the wave speed. And then what's part C? Create these plots yourselves. And what I have done is I used A equals 10. And B equals 10. And now that we know the units, we could include the units on there. So what you could do is you could literally make a table of times in Excel. And crank this out. And then what you could do is you could punch in. You could put whatever time you want here. I guess what did we use? 1.33. Ah, I screwed up, didn't I? Let me just say this again. You're trying to make the plot. What are our axes? X and Y. So you need a table of X and Y. I'm sorry. Right? But then, and so maybe we go 0, 1, 2, all the way out to 100 meters. But then here, you have to remember when you plug this equation in, you have to plug in A and B, but we also need to plug in the right value of V and the right value of T, which for the top graph, you'd use this time. For the bottom graph, you'd use this time. And I know this probably seems a little bit stupid to try and make the plots when you say, oh, I could just stick it all in Desmos and have the computer do everything for me, or Wolfram Alpha. I think you learn something when you have to make the plots yourself. Plus, it makes you more useful in lab because you're quick with Excel. So actually make those, you can see the results, they're right there on the page. Give that a shot.